You are watching DHTV from California State University, Dominguez Hills.
Hi, I'm Dr. Pamela Kreiser, and welcome back to NCR 507, which is our course on research, design, and interpretation. Now, today we are going to continue to lay the foundation for the numbers we look at and analyze in this particular class. And as we look at the numbers, that means that we have to start talking about some basic areas of statistics. So today's show will be covering two main areas. One are the basic principles of statistics, and then the second will be to look at experimental design. Now let's start with the first topic, looking at the basics of statistics. When we talk about one of the most fundamental concepts, we would identify the concept of descriptive versus inferential statistics. Now, what I mean by that is, are you describing the data or are you inferring from the data? Now, you might say you're not sure which one that you do. So let's take an example of a college class. Let's think about a class where everybody took a test and we had all of the frequency data related to that test. So everybody took the test, and then we take the set of data, or the test scores, and we analyze them for basic statistics. So we would look at the mean, the median, the mode, the standard deviation, the variance, and the range. Now we would look at all of those, and let's say we were only interested in summarizing the results of the class. We would say that as we were summarizing the test scores, we are doing what's called descriptive statistics, meaning we're not planning to use those scores to prove anything to anyone or to make other assumptions. We're simply just describing what happened when everyone in the class took that test. Now, in contrast to descriptive statistics is the notion of inferential statistics. And this is the idea that I would take a sample of some kind and then infer to a greater population, therefore engaging in an inferential process. Now, when we talk about inferential statistics, we're suggesting that we are sampling on the one hand and then inferring to a different population. Let's think about my same example regarding the test scores. When we have test scores and we have them for one class, I might believe that that represents a very good sample of, say, all of the classes that occur at a university. So I could decide to take that sample and infer that those reported frequencies are the same for the greater population. Now, it doesn't mean that it is, but those are the two processes. So the question is, are you summarizing the data or are you inferring from the data? They're two very different processes. Now, one of the researchers you have already seen in this course is Hans Rosling, and he is a very famous descriptive statistician. He does a lot of worldwide statistics, and you've seen his TED Talk with his son Ola, where they talk about what they can infer from statistics or what they all mean. So I want us to take a look at one of Hans Rosling's descriptive statistics TED Talks, where he summarizes 200 years of data.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
As you can see, Rosling does a fantastic job summarizing the 200 years of data that he's displaying for us in the high-level visual graphics that you saw. Now, when we think about displaying data for people, what we're doing is we're describing what's going on in the descriptive example, and we're helping individuals visualize what the data represent. Now, of course, that means that you as the researcher have to make lots of decisions about how you want to display your data. And as you make this series of decisions, of course, you have lots of things to think about. One of the main distinctions we've already talked about is this notion of continuous and categorical data. When we think about those two variable types, we know that when we're displaying the data, of course, we can use certain designs for continuous and certain designs for categorical. Let's take a look at this next clip talking about how we display data.
In this video, we will be talking about bar charts, pie charts, histograms, stem plots, and time plots. We can use these tools as a way of displaying data. We often use bar charts and pie charts to display categorical data, and we often use stem plots, time plots, and histograms for displaying quantitative data. Pie charts show the relative size of each value in relation to the whole. On the other hand, bar charts display the frequency on one axis and the values of the categorical variable on the other. You can think of bar charts as a way of tallying information. For quantitative data, we often use stem plots, histograms, and time plots to show information. We'll talk about histograms first. After collecting data from a population or sample, we can use a histogram to help us display the distribution of the data we collected. The frequency, or count, is displayed on one axis, and each count tells us how many data values fall within a predetermined interval on the other axis. This axis corresponds to the variable we have just measured. To read a histogram, you first pick one of the intervals and determine its height. So for the interval between 100 and 110, we see that the bar has a height of 8. This means that, from the data we collected, 8 people weigh between 100 and 110 pounds. For the next interval, we see that the bar has a height of 16. So this means that 16 out of the total people I collected data from weigh between 110 and 120 pounds. The rest of the histogram can be read in a similar fashion. A histogram is a form of a frequency distribution. Frequency distributions can be written in a table format, and they tell us how many data values fall within a certain interval. These intervals can be a little confusing. For example, if I recorded an individual's weight to be exactly 120 pounds, do I include them in this interval or this interval? By convention, we say that each interval does not include the right endpoint. So 120 is not included in this interval, and 130 is not included in the other interval. So in fact, 120 belongs to the second interval. Now you might be thinking, if the right interval isn't included, why don't I just rewrite my intervals like this? 110 to 119 and 120 to 129. Now the problem with this is that we don't have continuity. For example, if you weighed 119.7 pounds, there would be no interval that contains this value. Now a frequency distribution can be converted into something called a relative frequency distribution. The only difference between these two is that a regular frequency distribution shows a count, and a relative frequency distribution, as the name suggests, shows the relative frequency instead. It is called relative frequency because it represents the proportion of values in each interval in relation to the whole. To convert a frequency distribution into a relative frequency distribution, we will need to do some calculations. We start off by finding the total number of data values, and we do this by adding each frequency. We find that the total sum is equal to 50. Then, we will take each value and we will divide it by that sum. And as a result, we get the relative frequency values. To check if you have made the right conversions, you can add up all the proportions for each interval, and the sum should be equal to 1. The answer should be equal to 1 because we have used a ratio that relates our data to the total amount of data values. Because of this ratio, relative frequencies can be written in percentages. To convert to percentage form, all we do is multiply each value by 100%. In the same way, regular histograms can be converted into histograms that tell us the proportion of values for each interval. Now stem plots are like histograms, except they show each data point. Stem plots consist of stems and leaves. A leaf refers to the very last number, and a stem refers to all of the other numbers except the last number. Stems and leaves are usually separated by a line. For example, let's look at the number 117. The leaf is the last number, so this would be 7. The stem is all of the other numbers, so the stem is 11. On a stem plot, this would be written as so. Now let's look at the number 69. Using the same rules, we would get a leaf of 9 and a stem of 6. And on a stem plot, this would be written as so. Now when we have a string of leaves like this, it just means that I have the data points 30, 31, 32, 35, and 35. Notice how stem plots are constructed. Stems go down from low to high, and leaves extend outward from low to high. Depending on the dataset we are working with, sometimes we can get stem plots with too many leaves and we can get stem plots with too many stems. When this happens, we might not get a nice picture of the distribution, and as a result, we may not be able to get much information out of it. If we have a regular stem plot with too many leaves, we can convert it into something called a split stem plot. This conversion is called splitting the stems. To split the stems, we need to duplicate each stem. The first stem will run from 0 to 4, which corresponds to these values. And the second stem will run from 5 to 9, which corresponds to these values. The same logic can be applied to the rest of the stems. When we have too many stems, we can reduce the amount of stems by trimming the leaves. In this example, we have a very large dataset that goes from 201 all the way to 875. That's over 60 stems that we have to write. To trim the leaves, all we do is remove the very last digit. So notice for the number 201, the leaf is 1 and the stem is 20. After removing the very last digit, we get 20. So now the leaf becomes 0 and the stem is now 2. We would do the same process for each data value. By trimming the leaves, we get a better looking stem plot. Notice how we have reduced the amount of stems by doing this, and we have saved ourselves the trouble of having to write down over 60 stems. This is why trimming can be useful, but be careful when you read the stem plot after it has been trimmed. For example, for the top row, instead of reading it as 20, 20, 21, 22, 23, and so on, we read it as 200, 200, 210, 220, 230, and so on. This is because the original data was in the hundreds place. Now the last type of stem plot we will be looking at is called a back-to-back stem plot. Back-to-back stem plots are used to display and compare two distributions by using the same set of stems. So for example, we could compare data from males and females, or data from cats and dogs. Another way to display quantitative data is by using a time plot. Time plots show how a variable changes over time. By convention, time is always plotted on the x-axis, and the values of a variable are always plotted on the y-axis.
Now, one of the very common ways that we see data displayed is through the use of histograms. And when we think about histograms, they're really a way to show categorical information. Now, sometimes we superimpose a normal curve on those histograms to show how the data are laid out. And in that example, sometimes we actually use continuous data to look at the normal distribution and then perhaps a different distribution that we have. Now, when we're thinking about all of those terms, I want to back up a little bit and make sure that we're on the same page when we're talking about what all of those terms mean. So first, I want to talk about some measures of central tendency. And those are terms that you've likely heard. We have three that we tend to think about. We have the mean, the median, and the mode. And when we talk about the mean, the median, and the mode, these are ways to describe what's going on in the data that show us the mean, the average score, the median, the middle score, and the mode, the most frequently reported score. And all of those are indicators for me as a researcher. When I look at them, I can learn lots of things about the sample that I've collected. So as you think about those notions of central tendency, we know that they are familiar to us and they help us have more understanding. Now, when we think about other basic statistics, of course, we would think about measures of dispersion. And when we think about that, we would identify three different areas as well. We might be interested in the range, we might be interested in the standard deviation, as well as the variance. Now, let's go back and talk about range. You may have, in your earlier education, been taught that the range is one number to another number. So let's say the scores range from 1 to 9. Some of you were raised hearing that the range is 1 to 9. But actually, we would not say that. We would say when you calculate the range, you're calculating a numeric indicator of that range. What does that mean? You take your highest score, subtract your lowest score, and then you get the range. So that means that from a data set that ranged from 1 to 9 on a dimension, we would say the range is 8. 9 minus 1 is 8. Now, variance is a very important concept. And all this really means is how varied are the scores. So when you think about variance, just think about varying scores. When we talk about variance, we know that the other close stat that is related to variance is the standard deviation. And this is that same indicator of how varied the scores are, but just in standard measurement. So you would think of variance and standard deviation as giving some of the same information. Now, when we think about the range and the variance and the standard deviation, we know that all of that gives us information about dispersion. Now, think about what that means. Dispersed, how spread out. So I know the range, I know the lowest to the highest score. I know the variance, which is how spread out those scores are. And then I also know the standard deviation, which is just the same thing as the variance, but just in standard measurement. So let's take a look at this next clip where we identify some of the details about the standard deviation.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation. For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01. How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected, or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line. The 68-95-99.7 rule tells us that about 68% of the data fall within one standard deviation of the mean. About 95% of data fall within 2 standard deviations of the mean, and about 99.7% of data fall within 3 standard deviations of the mean. The average height of an American adult male is 5'10", with a standard deviation of 3 inches. Using the 68-95-99.7 rule, this means that 68% of American men are 5'10", plus or minus 3 inches. 95% of American men are 5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches. So, this means only about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7", and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results that are 5 standard deviations above or below the mean. A result that varies this much can signify a discovery, as it has only a 1 in 3.5 million chance that it is due to random fluctuation. In summary, standard deviation is a measure of spread. Along with the mean, the standard deviation allows us to determine whether a value is statistically significant or part of expected variation.
One of the projects that we've done in this course so far is to collect frequency data. And you participated in this if you're in the class, to put your scores of some different demographic information into a matrix. Now, if we took just age as an indicator, we could take an average score of that age, and we could also get a standard deviation, we could get range, all those different things in terms of analyzing it for frequency information. So let's think about our class. For this particular semester, the average age of those who are attending the class online that is related to this particular course, we know that the average age is 37.96. We also know that the standard deviation is 10.71. Now you might say, well, how do you know this information? I just ran it through a statistical program, SPSS, real quick, and got those answers. Now, the thing that's interesting about that is that we actually know quite a bit of information when we look at something like a mean score and a standard deviation. So one of the questions you might ask is, well, is everybody in their mid-30s? And the answer would be no. We can tell that from the standard deviation. So take a look with me at the standard deviation and the mean score, and let's learn about what we can identify about our class. Remember, we're again describing what's going on in the class. So we look at the mean score, and let's round that up and say it's about 38. And let's also round the standard deviation up to about 11. So what does that mean? That means that the average age is about 38. And then we also know from principles of standard deviation that if we moved up a standard deviation and down a standard deviation, we would capture about 68% of our particular class. Now, what does that mean? If you take 38 and you subtract 11 and add 11, you get that range of 27 to 49. What does that mean? 67% of our class, approximately, or 68%, range in age from 27 to 49. Now let's go out one more standard deviation. If we go 2 standard deviations out, meaning we take 38 and subtract 11 twice, and 38 and add 11 twice, we get 96% of our class population. And that means that our age range ranges from 16 to 60. Now you might say, wow, that's quite a range. How did you get the standard measurement units for understanding like how much of the population falls within 1 standard deviation or 2? And that's actually something that a statistician has already figured out for us. When we look at stats, we know that there are a number of principles that statisticians have identified for us that help us understand these concepts. So when you're thinking about any time you see a mean score and you see a standard deviation, you don't just know the average age, you know actually a lot more about the data. Now, this brings us to a larger conversation about this important identifier called the normal distribution. Let's take a look at this next clip and learn about that.
All right, I want to show you what a normal distribution is all about in statistics. And there are 3 things that should come to mind when you read the words normal distribution. The first thing is that you have what's called a bell-shaped curve that basically looks like this right here. It's bell-shaped curve, okay? That means that the mean, which is kind of sitting right here in the middle, has the most data that's sitting around it on either side of the mean. I'll talk a little bit more about that later. But definitely bell-shaped curve is one of the first things that should come to mind when you read that word normal. The second thing that should come to mind when you hear normal distribution is that the total area under the curve is equal to 1. So all of this area underneath this bell-shaped curve, all of it, including everything out here in the tails as they get smaller and smaller, is a total area of 1. And there's one more thing. The third thing that should come to mind is that this bell-shaped picture here is symmetrical, right? It's symmetrical. And that comes into play and is very handy. It's kind of a geometric term for later problems. So if I was to kind of split this thing right down the center here, you would see that half of this picture over here, if the whole thing is 1, is 0.5, and the other half is 0.5, giving you a total area, everything from here all the way over to here, right, total area all together, everything under the curve here, that gives you a total area of 1. So those 3 things should come to mind when you hear the words normal distributions. Bell-shaped, total area is 1, and it's symmetrical. Let me just go one more step and show you what I mean by, and perhaps you've seen this as well, not only are we talking about now a normal distribution, but something called a standard normal distribution. So a normal distribution, again, are these 3 things, right? Bell-shaped, total area is 1, and symmetrical. Standard normal kind of uses these 3 things, but kicked up one more notch, and 2 other things, we'll mark them 4 and 5, how's that? 2 other things should come to mind when that word standard is used, all right? 2 other things should come to mind. Number 1 is that the mean, and that Greek letter is mu, which stands for population mean, or population average, same thing, that the mean is going to be a 0. All right, that's what standard means. Standard means that the mean, population mean, is 0. And the other thing that it means is that this Greek symbol sigma, which is lowercase sigma, and that means population standard deviation, is automatically 1. So these 2 things are also part of what the standard normal distribution areas, right? So there's normal distribution, which means these three things. We covered those a second ago. But when you read the word standard normal, these two things also come into play, which means, going back to this picture here, that the mean sits right here in the middle, is 0. The average is going to be 0, and that one standard deviation, right, one standard deviation in either direction is also into play. So that's what we mean, and there's this other idea called the empirical rule, but we can get into that another time. 68% of your data is sitting smack within one standard deviation. But this is what, just a real rudimentary level of what we mean by a standard normal. Means that the population mean is 0, population standard deviation is 1, and when we say normal, we mean it's bell-shaped, total area is 1, and it's symmetrical. Hope that helps.
Now, you saw some information about the standard deviation, and that helps you understand about how that works. Now you've also seen the normal distribution. Now, when we're thinking about statistics, one of the areas you hear about all the time is statistical significance. Like, is something significantly different or not? And I hear this phrase all the time in my work. Was there a significant difference? Now let's think about the age ranges that we talked about and the standard deviations that indicate the dispersion of those ranges. We might ask the question, are you significantly older than the rest of the class? And when we look at the data that we analyzed right before this last clip, we would identify that you'd have to be under 16 years old to be considered special, and you'd have to be over 60 years old to be considered significantly older than the class. So think about it that way and say, wow, that means that that information actually helps me understand what I'm saying. Now, you might have been previously educated in statistics. And one of the, there's two different ways that we identify statistical significance. One is the traditional method, and the other is the p-value method. Now, the traditional method is where we use something called a critical value, and we go to a chart and understand using the critical value whether our results are significant. But you actually are operating in an age where technology is very helpful. And so our class will be following what we call the p-value method, meaning that we're looking at instances where something is significant if the p-value is less than 0.05. And so you might have heard that phrase before, p is less than 0.05, or perhaps you've seen in a study, p is less than 0.01 or 0.001. That is what we're talking about, this idea that the p-value helps us know if we have special information. Now, as we look at this next value, let's explore more about the p-value.
All right, in this video, I want to show you the basics of hypothesis testing for the non-traditional method, or the p-value method to be more specific, all right? The p-value method. I have shown in a separate video the basics of hypothesis testing using the traditional method. So there are two different kinds. Actually, probably more than two, but I'm only showing you two in my videos. So real quickly here, the basics of hypothesis testing, no matter what method you're using, traditional or p-value, is that there are going to be two types of hypotheses, right? There's the null hypothesis and there's the alternative hypothesis. Let's see, almost every book I've used uses H sub 0 or H naught as the null hypothesis, and no matter what parameter you're talking about, whether it's a proportion or a mean or a standard deviation, the null hypothesis always uses an equal sign, right? Always has an equal sign in it. The alternative hypothesis, maybe your book uses H sub 1 or H sub A, whatever the case may be, always uses a symbol that is not an equal sign, right? So in this case, it's a less than symbol or a greater than symbol or a not equal to symbol. But no matter what type of hypothesis testing this is, you will always be given some level of significance here, okay? So whether it's 0.01 or 0.05 or 0.10, something like that. Now that level of significance is called alpha, right? It's called alpha, which is the Greek lowercase letter A here. That's the first letter of the Greek alphabet. And we're not restricted to 0.01, 0.5, or 10% or something like that. It could be any other type of level of significance, but these are the three more popular ones. Okay, the other thing I want to tell you about, and keep your eye on these three alternative hypotheses here, right? So less than, greater than, or not equal to is, depending on what kind of a test we're talking about, you might have a left tail test, a right tail test, or a two tail test. And that all depends on the alternative hypothesis. So I'm using H sub 1 as my alternative hypothesis notation here. But if the alternative hypothesis is less than, we have a left tail test. If it's greater than, we have a right tail test. Or if it's not equal to, we have a two tail test. We have a two tail test. So that is also important and significant here. And what do I mean by that? I didn't show this in my previous video, but for example here, let's say I got a little package here of push pins. Can you guys see that? I think you can see that in the video here now. All right, and it says that there should be 100 push pins in here. Now, if I think I got gypped, right, and I'm thinking they're putting less than 100 push pins in there, then less than would be a left tail test. All right, or maybe I'm thinking they're being generous as I buy these push pins, and they're actually putting more than 100 in. Well, more than would be a right tail test, greater than. Okay, or if I state the claim, right, all of these are claims here. If I state the claim as, I don't think they're putting 100 in there. Right, notice I'm not specifying when I say I don't think they're putting 100 in there. I believe there aren't 100 in there. I'm not specifying whether it's less than 100 or greater than 100. So in that case, it would be a two-tailed test. So depending on the wording that you see, it could be one of those types of alternative hypotheses or claims. Okay, so what I showed again in a previous video, you could look it up, is the traditional method. And what I'm going to show you in this video is the p-value method, right? But notice I wrote on this little piece of paper here that both methods, doesn't matter which method you're using, both methods require you to find a test statistic. So both methods use a test statistic. Whether your test statistic is with proportions, that would be p hat minus p over the square root of little p times q over n, or maybe you're dealing with sample means and population means, and so your test statistic would be with this formula here. So you probably are familiar with those formulas, okay? But regardless of the method, both of them use test statistics, okay? So what the p-value does, separately from the traditional method, is this, all right? The traditional method uses something called critical values. All right, I'll just put this on here real quick. The traditional method uses something called critical values. Well, guess what? And I'm going to cross that out. The p-value method does not use that at all. All right, p-value method says, look, I don't really care about the critical value whatsoever. So that's kind of a nice little thing here. So let's say that, for example, we were dealing with a right tail test. All right, so I'll draw a little right tail here. Right. So let's say, for example, we were dealing with a right tail test. That's our h sub 1 is a greater than. Then what the p-value says is this. All right, what the p-value says is this. What we're going to do is we're going to find, using the formulas that I just showed you a second ago, we're going to find, put here find, we're going to find our test statistic. All right, we're going to find our test statistic using that formula you just saw on the previous page. And then we're going to put that in. I'm going to write this as how about TS? All right, test for statistic. We're gonna put that in here, and this is a right tail test. Let's say our test statistic here. I don't know. I'm just kind of making something up. But let's say our test statistic came out to be something like how about negative 2.61, for example. All right. Or sorry, positive. This is on the right hand side. So let's say our test statistic came out to 2.61. Okay, so for example here, 2.61. Now, do you see that this area, the area sitting over here to the far right of this, is 0.0045. Okay, you can look that up. This area is 0.0045, right? It's 0.0045, and you can look that up on a table if you want to, or you can use Excel to figure that area out. But here's the deal. That area is what's called our p-value. All right, so this area is the p-value now. All right, so the area sitting over here to the right, in this case of a test statistic, is our p-value. Okay, so that area, in this case 0.0045, is our p-value that we are going to compare. Right, we're going to compare the p-value to our alpha, to our level of significance. And that's how p-value method, the testing, works. So in our case, I have a p-value of 0.0045, and let's say that we had an alpha. Let's say that we were looking for a level of significance of 0.01, for example. I don't know, we'll pick on 0.01. All right, so our alpha, our p-value is sitting right here. Our alpha is sitting right here of 0.01. And as you compare these two, do you notice that this one here, our p-value, is less than 0.01? All right, and there's a phrase that goes along with this. If the p-value is low, right, lower than my alpha, my level of significance, then the null must go. So we're going to take the null hypothesis and we're going to reject it. Right, we're going to reject it. What if, though, let's just say, for instance, what if our p-value was greater than our alpha? All right, I know this is not the case in this particular case, but let's say we had a p-value of 0.0289, something like that, right? And in this particular case, look, our p-value rather, would be bigger than our alpha of 0.01. So if this is the case, if your p-value is high, right, is larger than your alpha, then the null must fly. So we're going to keep, right, the null hypothesis. So hypothesis testing is all about the null. We either reject it or we, in my case I put keep here, but technically the term is we fail to reject. Okay, so this is a reject here if the p-value is low, and if the p-value is high, then the null must fly. What we're really doing is we are really failing to reject. That's what's going on here when I say the word keep. Okay, we're failing to reject. So if the p-value is low, the null must go. If the p-value is high, the null flies. And what that really means is, if we reject the null hypothesis, what we're in essence saying is we support the claim of the alternative hypothesis. Right? If we keep the null hypothesis, what we're in essence saying is this may be true, therefore we don't have enough evidence to support our claim. Right? So the wording of this is pretty tricky. You've got to get your mind around that as well. But this is how p-value testing works.
When we talk about the p-value, we are identifying one important notion, and that's the idea that if something is significant, we're suggesting actually that it's different than 95% of the rest of the data. And that's kind of an interesting way to look at it. Is p less than 0.05, meaning that it's different than 95% of what you've already collected? So that's a way to think about significance testing. Now, in the video, they talked about a concept about the p-value and what you do regarding the null hypothesis. Remember, the null hypothesis is this notion that there is no difference. So if we look at the phrase that they made in the video, if the p-value is low, the null must go. So we reject the null hypothesis. What are we doing in that first case? We're saying we have a significant finding. And then if the p-value is high, we know the null must fly, meaning we have failed to reject the null hypothesis, or meaning that we didn't find anything. Now, when we think about hypothesis testing, we start with the assumption of the null hypothesis, as you already know. And then when we find results where we can reject the null, then we're saying we have something very special in our results. So that's kind of an overview of the p-value method and also the notion behind significance testing. We're looking to see if we have any special information. The next part of our show is to explore the concept of experimental design. And this is the notion that the researcher controls aspects of the experiment and uses special parts of design in order to control for variables and to rule out other explanations. What are we trying to do? We are trying to assign causality. Now, you might say, what does that mean to assign causality? What I would say is we can't prove it 100%, so we're trying to reduce the error that takes place in the experiment so that we can rule out other explanations and isolate what we believe could be assigned as a causal function. Now, as we think about it, you might say, well, let me think, I've heard these different things about experimental design, and I would tell you that before you explore any aspect of experimental design, it is important to understand the difference between true and quasi-experimental design. Now, what does that mean? That means that true experimental design has random selection, and quasi-experimental design does not. Now, what does that mean? Random selection means that how I slot into my study, whether that's people or how people are exposed to treatments, all of the processes that I use are truly random, then I have a true experimental design. But if I don't use true random procedures, then I have a quasi-experimental design. Now you might say, well, what does that mean to say true? And what I would say is when we say someone is in a true experimental design, that means that the participant has an equal chance of being selected. It's truly random. They could be in treatment level A, treatment level B, it's all randomly assigned. And even the assignment to the study is random, such that all of the members of the population where they're drawing that sample has an equal chance of being selected. So just think the phrase equal chance of being selected being your guide to whether you think you are involved in a true experimental design or a quasi. Now, we use true experimental design and quasi-experimental design for a bunch of different reasons. And so you can read about some of those reasons. Sometimes we save money by doing quasi-experimental design. It just depends. We see in a lot of drug testing, we see a lot of protocols that are related to this, where we might use different designs to save us money, which are maybe not random, so they wouldn't be true experimental design, but maybe quasi. But then when we're trying to really assign causality, doing the true diligence, we would have something called true experimental design. So the next video I want us to take a look at explores a couple of important concepts in experimental design.
In this video, we will be talking about the placebo effect, control groups, and the double-blind experiment. A placebo is known as a fake treatment. It could be known as a fake pill, drink, lotions, or any type of treatment that is known to have no medical effect. However, a placebo may have psychological effects. These psychological effects are known as the placebo effect. By believing and expecting something to work, it will work. For example, if you believe that a pill will make you feel better, then it will make you feel better, even if the pill is fake. In other words, the pill is a placebo. If you think that the same placebo will make you feel sad, then it will make you feel sad. This is the placebo effect. Placebos can be used for a control group. The control group receives the placebo as a treatment. In other words, the control group receives a fake treatment. Now, why would you want a control group? A control group gives you something to compare your results with. So suppose an unknown company were giving pills to people at the gym to help them gain strength. After 1 month of treatment, 75% of the people taking the pills report that their strength has increased. Does this mean that the pill was the cause? No. So far, this is an observational study. We cannot say for sure. Maybe there are lurking variables that are present, like diet and the type of workout routine. Some people may have better diets or workout routines, which may have allowed them to become significantly stronger than everyone else. This is why we need a control group. We could randomly assign participants into 2 groups. One group will be the control group, and the other group will be the experimental group. Each group will have to get the same thing. So each group will receive the same diet, each group will have the same workout routine, and each group will get the same amount of sleep, and etc. The only thing that is different between these 2 groups is that the experimental group receives a pill and the control group receives a placebo. A good placebo should look and taste like the actual pill. If the percentage of people in the experimental group significantly gain more strength than the people in the control group, then we can say that the pill is actually the cause for gaining strength. You can think of the control group as just doing nothing to it. We have the placebo for humans because we can perceive things psychologically. If instead our experimental units were plants, which lack a nervous system and the ability to perceive things psychologically, then we don't really need a placebo. So the experimental group of plants receives the treatment and the control group gets absolutely nothing. And then we would compare the results from the experimental group and the control group. Going back to our first example, If the control group knows that they are receiving the placebo, then this will obviously eliminate the placebo effect and it may skew the results. We need an equal playing field, where neither group knows if they got the placebo or if they got the actual treatment. To prevent bias in the manipulation of results, the experimenter should also not know which group is which. This setup is called the double-blind experiment, where the experimenter and the subjects do not know which of the groups being studied is the experimental group and which of the groups is the control group. The double-blind experiment is good for eliminating biased research results.
So you can see that using placebo or controlling for variables helps us rule out unintended effects or other effects that might be affecting the data in our study. Let's take a look at a more detailed clip on placebo effect from TED Education.
In 1996, 56 volunteers took part in a study to test a new painkiller called Trivaricaine. On each subject, one index finger was covered in the new painkiller, while the other remained untouched. Then, both were squeezed in painful clamps. The subjects reported that the treated finger hurt less than the untreated one. This shouldn't be surprising, except Trivaricaine wasn't actually a painkiller, just a fake concoction with no pain-easing properties at all. What made the students so sure this dummy drug had worked? The answer lies in the placebo effect, an unexplained phenomenon wherein drugs, treatments, and therapies that aren't supposed to have an effect and are often fake miraculously make people feel better. Doctors have used the term placebo since the 1700s, when they realized the power of fake drugs to improve people's symptoms. These were administered when proper drugs weren't available, or if someone imagined they were ill. In fact, the word placebo means "I shall please" in Latin, hinting at a history of placating troubled patients. Placebos had to mimic the real treatments in order to be convincing, so they took the form of sugar pills, water-filled injections, and even sham surgeries. Soon, doctors realized that duping people in this way had another use: in clinical trials. By the 1950s, researchers were using placebos as a standard tool to test new treatments. To evaluate a new drug, for instance, half the patients in a trial might receive the real pill. The other half would get a placebo that looked the same. Since patients wouldn't know whether they'd received the real thing or a dud, the results wouldn't be biased, researchers believed. Then, if the new drug showed a significant benefit compared to the placebo, it was proved effective. Nowadays, it's less common to use placebos this way because of ethical concerns. If it's possible to compare a new drug against an older version or another existing drug, that's preferable to simply giving someone no treatment at all, especially if they have a serious ailment. In these cases, placebos are often used as a control to fine-tune the trial, so that the effects of the new versus the old or alternative drug can be precisely compared. But of course, we know that placebos exert their own influence too. Thanks to the placebo effect, patients have experienced relief from a range of ailments, including heart problems, asthma, and severe pain, even though all they'd received was a fake drug or sham surgery. We're still trying to understand how. Some believe that instead of being real, the placebo effect is merely confused with other factors, like patients trying to please doctors by falsely reporting improvements. On the other hand, researchers think that if a person believes a fake treatment is real, their expectations of recovery actually do trigger physiological factors that improve their symptoms. Placebos seem to be capable of causing measurable change in blood pressure, heart rate, and the release of pain-reducing chemicals like endorphins. That explains why subjects in pain studies often say placebos ease their discomfort. Placebos may even reduce levels of stress hormones like adrenaline, which can slow the harmful effects of an ailment. So shouldn't we celebrate the placebo's bizarre benefits? Not necessarily. If somebody believes a fake treatment has cured them, they may miss out on drugs or therapies that are proven to work. Plus, the positive effects may fade over time, and often do. Placebos also cloud clinical results, making scientists even more motivated to discover how they wield such power over us. Despite everything we know about the human body, there are still some strange and enduring mysteries, like the placebo effect. So what other undiscovered marvels might we contain? It's easy to investigate the world around us and forget that one of its most fascinating subjects lies right behind our eyes.
Now, you might be wondering why we're talking about controlling so much or talking about the placebo effect. And the very simple answer is that when we study or explore investigations that involve humans, we are at risk for unintended effects. That's the bottom line. And so when you're thinking about your research, that when you have a situation where humans are involved, it's just important to have controls in place so that you can isolate any unintended effects. Now, the next clip talks about some basic types of experimental design. Here we're going to identify randomized design. We've talked about the idea of randomization. We'll talk about randomized block design and also matched pair design.
In this video, we will be looking at experimental designs. The types of experimental designs include the completely randomized design, the randomized block design, and the matched pairs design. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. Each unit in the same group will receive the same treatment, and at the end of the experiment, you will compare the results from each treatment. Show how a completely randomized design would be used in the following example. A researcher wants to conduct an experiment to determine which environment is best suited for studying: a library, in one's own room, or outside. A total of 30 university students volunteer to participate in the experiment. So we have 3 treatments: the library, in one's own room, and outside. Since we have 3 treatments, we will have 3 groups receiving the treatments. Since there are 30 university students, these 30 subjects will be randomly assigned into 3 groups to receive the treatments. Since there are 30 people, each group will have 10 people, and at the end of the experiment, we would compare the results from each treatment. Let's say that the researcher believes that gender has an effect on the results. In a case like this, we would use a randomized block design. A randomized block design doesn't immediately randomly assign experimental units to receive treatments. We first assign people into a block based on a characteristic that is expected to influence the response to the treatments. In this example, gender would be the blocking variable. So first, we separate our experimental units based on gender. One block will be for females and one block will be for males. There are 18 females and 12 males. Then, the experimental units in each block will be randomly assigned to 3 different groups to receive a treatment. So let's make a diagram out of this. We are looking at a randomized block design, and gender was the blocking variable. We started off with 30 university students, and we separated these students into 2 blocks. One was for males and one was for females. We determined that there were 18 females and 12 males. We will have the females be randomly assigned to 3 different groups, and each group will have 6 females, and each group will receive different treatments. For the males, we are doing the same thing, except we have 12 males, so we will randomly assign 4 males into each group. And at the end of the experiment, we will compare the results within each block. The last type of experiment we'll talk about is the matched pairs design. In a matched pairs design, we are only comparing 2 treatments by using the same or similar experimental units. If we are using the same experimental units, we could have an example like this. What type of gasoline is more efficient? Type A gasoline or Type B gasoline? 3 cars will be used in this experiment. Describe how a matched pairs design would be used. If we are using the same experimental units, then each experimental unit will receive both treatments. So we have 3 cars, and each car will receive the 2 treatments, one with Type A gasoline and one with Type B gasoline. We would use the same car for each treatment, and which treatment goes first will be random. So for example, we could drive with Type B gasoline first, then once all the gasoline is finished, we would fill up the car with Type A gasoline using the same quantity, and at the end of the experiment, we would compare the efficiency of the gasoline. There are cases when we can't use the same experimental units for a matched pairs design, and we would have to use similar experimental units. For example, a researcher is trying to determine whether or not sleep deprivation has an effect on test scores. Describe how a matched pairs design would be used. Well, we could try giving both treatments to the same experimental units like we did in the other example. In other words, we could have the same person write the test on 2 different days, one being sleep deprived and the other with sufficient sleep. The problem with this is that we can't have the same subject write the same test because they would know what's on the exam when they write it the second time, so that would be kind of unfair. Instead, we could start off by pairing up students with similar GPAs. So for example, the two students with the highest GPAs would be matched up together, and the two students with the lowest GPAs would be matched up together. Then, each pair will be split up and randomly assigned to one of the two treatments. So for a pair, one person will get the sleep-deprived treatment, and the other person will get a normal amount of sleep. Then, we would compare the results for each pair, and we will also compare all of the results. So for example, if we saw that the sleep-deprived people were consistently getting lower test scores than the people who got a regular amount of sleep, then we can say that sleep deprivation was actually the cause for a bad test score. So let's quickly recap. These are the experimental designs we talked about. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. This is what the diagram would look like. Group N, or treatment N, means you can have any number of groups or treatments. A randomized block design first assigns people into a block based on a characteristic that is expected to influence the response of the experimental units to the treatments. Then, a completely randomized design is performed within each block. This is what the diagram would look like. Block N means that you can have any number of blocks that you want. For a matched pairs design, we saw two scenarios, one that uses the same experimental units and one that uses similar experimental units. Both of these involve the comparison of only two treatments. If you are using the same experimental units, each experimental unit gets both treatments. This is what the simplified diagram would look like. If you are using similar experimental units, we first pair up similar experimental units, then each pair is split up and randomly assigned to one of two treatments. This is what the simplified diagram would look like.
Now, if you've done any work in experimental design, one of the ideas that you're probably familiar with is that there's so many designs out there. And you might think, well, I've heard of Solomon four-group design, or I've heard of randomized block, or all these different types of design. And as we're talking about this, I want to remind you that it's not necessary to memorize any of those designs. And the reason is that as you do your research, you have the ability to look all of that up and to execute on protocols that people have already helped decide that. And so what does that mean? You don't have to do the memory work. You just need to know that experimental design is out there and what it's doing. And then when you get to your experiment, you can look through the protocols that other people have done for you. So as we wrap up this notion of experimental design, it's important to make sure we wrap up two very important concepts. One is the notion of true versus quasi-experimental design. So we have true, which is the random selection, and quasi, the non-random selection. And then we also have the notion of assigning causality. This idea that why I do experimental design in the first place is to isolate unintended effects and to look at underlying causes so that I can assign it. I can't prove it, but I can research and rule out other explanations. So today we've covered a couple of important, bigger ideas. We've talked about the basics of statistics, and we've also talked about experimental design. Thank you so much for joining me today, and I hope that your day is not just different, but significantly different.